Today, we are going to examine the fundamental differences between two core computing models, sequential and parallel programs. As we build faster and more complex software, understanding how instructions are executed, whether one by one or all at once, is crucial for performance. Over the next 10 minutes, we will break down the definitions, compare their advantages and disadvantages, look at real-world analogies, and discuss the specific challenges that come with parallel computing. Let's start with the traditional model, sequential programming. By definition, this is a model where instructions are executed one after another in a specific, rigid order. To understand this, think of a single checkout lane at a grocery store. Even if there are 10 customers, the cashier can only process one person at a time. The second customer cannot be served until the first one is completely finished. In terms of hardware, this relies on a single processor core, and the flow of execution is strictly linear. If you look at the diagram on this slide, you will see a vertical stack starting with begin and ending with end. Notice how the arrows flow straight down. We have statement 1, followed immediately by statement 2, and then statement 3. There is no deviation here. Statement 3 physically cannot happen until statement 2 is complete. This illustrates the linear blocking nature of sequential programming. The advantages are significant. First, simplicity. It is much easier to design, write, and maintain code when you know exactly what line runs next. Second, determinism. The output is predictable. If you give it the same input, you get the same output, which makes debugging essentially easier. Third, low overhead. We don't waste resources managing communication between different cores. However, there are disadvantages. The main issue is speed. It is much slower for massive computational tasks. It also suffers from blocking. If one task is waiting for I/O, like reading a file, the CPU just sits idle, wasting resources. To ground this in reality, let's look at a washing machine. This is a perfect example of sequential programming because the steps are based on a timer or sensors and must happen in order. 1. First, you lock the door for safety. 2. Then, you fill the drum with water. 3. Only after it is full can you wash and rotate the drum. 4. Then you drain the water. 5. Then you spin. 6. Finally, you unlock. You cannot spin the clothes while the water is filling. That is sequential execution. Now, let's switch gears to parallel programming. Definition-wise, this model breaks a larger problem into smaller, independent subtasks that are executed simultaneously. Returning to our grocery store analogy, think of this as opening multiple checkout lanes. Instead of one long line, several customers are being processed at the exact same time by different cashiers. Hardware-wise, this requires multi-core processors or distributed clusters, allowing for a concurrent flow where steps A, B, and C run at the same time. Please focus on the diagram. We start at the top, but notice how the flow splits immediately after start. Instead of a single vertical line, we have 3 parallel branches. Statement 1, Statement 2, and Statement 3 are all sitting side by side. These represent tasks happening simultaneously. However, look at the bottom where they converge at the box labeled synchronization. This is a critical step where the system waits for all parallel tasks to finish before moving to the end. This visualizes how we split the work and then join it back together. The advantages: speed and efficiency. We drastically reduce execution time for large tasks. Resource utilization. We make full use of modern multi-core CPUs. Non-blocking. If one thread is waiting for data, the others can keep working, unlike the idle CPU in the sequential model. The disadvantages: complexity. It requires advanced knowledge of threading and memory management. Synchronization overhead. Paradoxically, the time spent managing the communication between these threads can sometimes outweigh the speed gains you hoped for. Let's apply this to a real-world scenario, a commercial kitchen. In a parallel program, you have a team of chefs, representing a multi-core processor. Instead of one person doing everything, Chef A chops vegetables. Chef B grills the chicken. Chef C boils the pasta. Chef D makes the sauce. They are all working at the exact same moment. The result of this kitchen approach is that all tasks happen simultaneously. The total time to cook dinner is significantly reduced. In fact, the dinner is ready in the time it takes to complete just the single longest task, rather than adding up the time for every single step. This is the technical equivalent of a multi-core CPU dividing a large task into chunks and processing them simultaneously. However, parallel programming introduces risks that simply don't exist in sequential programs. The first major challenge is race conditions. This occurs when two threads try to modify the same shared variable at the same time. The final result depends on who gets there last, which leads to unpredictable and incorrect data. Think of the analogy of two people trying to edit the exact same sentence in a Google Doc at the exact same instant. If you don't see each other's cursor, you end up overwriting each other's work and the sentence becomes gibberish. The second major challenge is deadlocks. This occurs when two threads act endlessly, waiting for each other to release a resource. The analogy here is a traffic standoff. Driver A refuses to reverse until driver B moves, but driver B refuses to move until driver A reverses. Because neither will yield, both are stuck forever. This diagram illustrates a circular wait. Look at the two main circles representing processes or threads. We see one arrow labeled waiting for and another labeled owned by. The process on the left owns a resource that the process on the right is waiting for. However, the process on the right also owns a resource that the process on the left is waiting for. It creates a closed loop. Neither can proceed because they are both waiting for the key that the other one holds. This loop is the definition of a deadlock. To summarize, while sequential programming offers simplicity and predictability, parallel programming provides the speed and efficiency necessary for modern computing. However, adopting parallelism requires us to carefully manage challenges like race conditions and deadlocks.